So, like I've said, I'm going to record all of our lectures, and I'm going to put all of our lecture notes into the content library. So, while you're more than welcome to take notes and write things down, it's all going to be, you're going to have my notes available to you, and you're going to have the video to go back and watch if you need to. So if you feel like you'd rather like sit and listen and pay attention and not worry about writing everything down, that's perfectly fine. If you feel like I can't sit and listen like without writing things down, like I'm just going to zone off and it's going to be like it helps me to stay focused to like physically write notes, do that. No big deal. And even if you want to experiment and try to figure out like what's really going to work best for you, like I think that's an important thing to figure out before in a year or two you're off in college trying to do this on your own, trying to figure out like, can I just sit and listen if I have all the notes already, or am I better off like writing things down and taking some of my own notes? So again, like I don't require you to do anything, and if you don't do it, like you have all my stuff as backup anyways. So just, feel free to experiment and figure out what's going to work for you. Okay with that? Okay. So in the content library, when I make a note, I'm just going to title the note with the date. So it's easy to tell, like, if you're absent, like, what was the day that were the notes, rather than by topic, because if you're gone a couple of days, sometimes it's hard to figure out, like, what topics you're looking at. So I'm just going to title them with the date. Okay. So this class, first semester, the emphasis is on this subject called trigonometry. And this is what my penmanship looks like. I apologize in advance because it's not great. My wife tells me I look like I have child handwriting. But this is what it looks like. If there's ever at a point that you can't read anything or you don't understand what a symbol is or whatever, please stop me and interrupt. Okay? It's no big deal. Like, I acknowledge that my penmanship is less than spectacular, and if you're having a hard time deciphering what it says, please stop me, and I will clarify and rewrite if I need to, and all that jazz. Okay. Okay. And again, like at any time when we're doing this, most of these lessons I'm going to do on OneNote with the projector. If it gets to a point where the light is an issue, you don't need to ask me. Just stand up and turn the light out. If it makes it easier to see what's going on, no problem. Or if you've been in the back and we're doing something and you can't see enough, like stand up and move. It's not a big deal. Okay? Particularly in this class, there's a lot of empty seats. So if you need to move around a little bit to see better, that's fine. You don't have to ask. Just do it. No big deal. Okay. All right. So back to topic here. This course is trigonometry. Now, if we're trying to decipher what this word trigonometry means, what do you see as like the root word here? Yeah, the trig part probably references triangle, right? And then what about like this ending, like a tree? Because you have things like chemistry and geometry and like, yes. I'm sorry, I couldn't. Metric? Okay. Not exactly. Yeah, like study of, right? Yeah. So really what trigonometry, the basis of this is like the study of triangles. So when was it, or in what course did we encounter a lot of dealing with triangles, and did we study triangles a lot? Geometry, right? So I know that's been a couple of years since we've been in our geometry class, but let's think back to that experience and think about some of the things that we remember regarding triangles. So when you talked about triangles in geometry, what were some of the important things that you talked about? Go ahead. Okay, so there's two SASs actually. So because there's two types of relationships between triangles. Right, side angle side, but there's two side angle sides. Because there's two ways that a triangle could be related. Do you remember those two different types of relationships? Anyone, not necessarily just, I already forgot, Josh. Not just Josh, who is successfully remembered side angle side. Absolutely. What did we use side angle side to prove? Congruence or similarity. Yeah. Exactly. Thank you. Those are the two types of relationships that I was looking for. And the symbol we used for similarity was just like that tilde, right? Okay, so what did it mean for two triangles to be congruent? Okay, and the sides are the same, right? So all the angles are congruent and all the sides are congruent. Do we remember what it meant if the two triangles were similar? Yes, sir. Okay. When you say they, what is they? Right. So it's not the triangle that shares the same ratio, but it's the triangle's side lengths. Good. So we'll say side lengths are proportional. Okay. And one other thing. The angles are congruent. Good. Okay. What else do we remember from geometry in regard to triangles? Yes, sir. Okay. So do you remember what those two special right triangles were? Good. Okay. Very good. What else? There's still one big thing that I'm hoping for. Yes. Tangent. Yes. Excellent. Does anybody remember the acronym we used to remember those definitions? Yeah, SOHCAHTOA. So when we used sine, cosine, and tangent, on what kind of triangle situations could we use sine, cosine, and tangent? Had to be with a right triangle, right? And what kind of angle are we using sine, cosine, and tangent on inside of that right triangle? The acute angle. I guess that's a little redundant, right? Can you have angles in a right triangle that aren't acute? No, why not? Yeah, because a triangle, the interior angles of a triangle add to 180 degrees. That was called the triangle sum theorem. Okay. So that's a little bit of a drawback here. One of the main focuses in trigonometry in this first semester is going to be using sine, cosine, and tangent. So what is this function? Let's focus on sine here for a moment, but it's really the same for any sine, cosine, or tangent. What is this function sine doing? What is sine doing? What is the input here for sine? What do we plug in for x?
Is it like the opposite side is over the hypotenuse?
Well, that's what the output is. That's what the output is. But what are we plugging in for x? An angle. Specifically, what kind of angle? It has to be an acute angle from a right triangle, right? With our geometry definition for this, yeah, we're going to take an acute angle and we're going to map that into a ratio of side lengths. Right? Is everybody okay with that? Specifically, the ratio we said was opposite over hypotenuse, right? One of you fellows over here mentioned that earlier. So an acute angle is bounded between what two numbers? Well, 1 and 89, you could have an acute angle that's 0.5 and 89.5. Yeah, so that value for x has to be between 0 and 90 degrees. And if I have a ratio of side lengths where we have opposite over hypotenuse, what two numbers is that going to be bounded between? It's a little bit trickier. Let me give you a hint. What do we know about the hypotenuse of the triangle? It's the longest side. So if I have a fraction where the biggest number is in the bottom, what is that fraction bounded between? So between two numbers, what's the smallest that fraction, or what number does that fraction have to be at least bigger than? 0, right? And what does that fraction have to be smaller than? Yes, sir. Not 90 degrees, because it's a ratio of two side lengths. Well, it's going to be much smaller than the hypotenuse, because the hypotenuse is the denominator of a fraction. 1, exactly. Right? Like if the biggest number is on the bottom of the fraction, it's always going to be a fraction that's less than 1, right? Like 7/9, less than 1. 5/10, less than 1. If the biggest number is on the bottom, the fraction is always got to be less than 1. Everybody's okay with that idea? Now, if you remember back from your algebra course last year, we talked about the definition of a function, right? Do you remember what that definition is? Yes, sir. Okay. It's that every element in the domain matches to exactly one element in the range. That's kind of what you said. You were more like 1-to-1, but I think I got what you're saying. So how do we know that any right triangle with acute angle alpha is going to have the same ratio of side lengths as some other right triangle with acute angle alpha? How do I know that this opposite and hypotenuse would be the same as this opposite over hypotenuse? Because that's what the sine function is saying. Like sine of 36 is always going to be this number, right? So you're saying that opposite over hypotenuse in this little tiny triangle is going to be the same as opposite over hypotenuse in this big triangle, right? Why is that going to be true? Yes. Okay. And when you say the angles are the same, what do you mean? So these angles are the same. Okay, what else? Okay, why is that one going to be the same? You're right. I just want to clarify as to why.
You have two angles, they all have to add up to 180.
Right. So in fact, what it really is saying is that these two angles are also the same, right? And that forces then these angles to be the same, right? So we have a triangle where 3 of the angles are the same. What does that tell us? Or 2 triangles where the 3 corresponding angles are all the same. Similar, right? Remember, the triangles similar can have different side lengths, but what has to be true about the side lengths? Yeah, they have to be proportional, which means that their ratios are the same, which is why opposite over hypotenuse in the small triangle is still going to be the same as opposite over hypotenuse in the big triangle, because those triangles are guaranteed to be similar. Everybody okay with that? So this was our geometry definition of sine, cosine, tangent. All work because we're relying on these triangle similarity going on in these right triangles. What if we want to extend our definition for sine to deal with something like sine of 100? Not using our geometric definition, right? Because if I draw a triangle with a 100-degree angle, I could draw another triangle with a 100-degree angle, and they're not guaranteed to be similar, right? Because in fact, can I draw a right triangle with a 100-degree angle in it? No. Why not? The triangle sum has to be 180 degrees, right? So if I have a right angle and a 100-degree angle, I have 190 degrees already, and that's a problem. Everybody agree? But if you type this into our calculator, we certainly get a number that comes out of this, right? So there must be a way to deal with this. That's one of the things we're going to worry about here in first semester, is how to extend our definition, our geometric definition for sine, cosine, and tangent to deal with obtuse angles. What else would we do? Well, what if we wanted to do sine of negative 10 degrees? This makes no sense in a geometric setting because what the heck does even a negative angle mean? We're going to extend our definition of what an angle means to define negative angles. And then as a result, we'll be able to deal with sine, cosine, tangent of negative angles. What about this? Not only is this an obtuse angle, but you can't even construct a triangle, any triangle, with a 230-degree angle in it, right? We'll be able to do sine of 230. We're going to extend our definition of sine, cosine, tangent, and remove the necessity to base this onto a triangle. So the goal here is, in geometry, our sine function mapped the interval 0 to 90 degrees onto the interval 0, 1, right? When I write this, this is not an ordered pair, correct? You guys remember interval notation from last year? Now, it looks exactly like an ordered pair, which is why I'm pausing to remind you guys what I'm doing. This means the same thing as the inequality, like 0 less than x less than 90 degrees, right? I just want to remind you what I'm doing here, okay? In trigonometry, we're going to extend this definition so that the domain for sine becomes all real numbers, and the range becomes anything between -1 and +1, including -1 and +1. Remember, again, from your algebra course last year, the difference between a parenthesis and a bracket. The bracket is like the or equal to inequality versus the parenthesis being the strict less than or greater than inequality. And now we're not going to get into how we're going to do that right now. And I've given you no inclination of like how we might extend the definition to do this. But what I want to point out to you is, notice that 0 to 90 is a subset of all real numbers, right? Our new trigonometric definition is going to include the geometric one, right? Similarly, 0 to 1 is a subset of -1 to +1, right? So this new definition is going to do everything the previous definition did, but it's going to handle more cases, which is what most of mathematics is, right? You start with a special case and find a rule that works, and then you see if you can extend it to something more general, and try to extend it again to something more general, till you get like the most general description possible. But typically, as you learn mathematics, you start with the special case, and then you build out to the most general one, because the general is usually more complicated than the special, which hopefully should feel familiar, right? When you learned how to factor polynomials, you started with a leading coefficient of 1, right? Like x squared plus 5x plus 6, which you learned was pretty easy to factor using a shortcut. But when you get something like 2x squared plus 3x plus 1, a little bit harder to factor that with the same kind of shortcut, right? We need to do a little bit more work to factor something like that out. Same idea here. Now, the technique you used to do with the leading coefficient still worked when the leading coefficient was 1, but it was more general, right? Covered other situations.
Fifth period here. Students, when you go out